Hello, good day everyone. Welcome to another session in our astronomy class. Phases and motions of the moon. The moon is the brightest and most obvious object in the sky. Unlike the sun, it does not shine under its own power, but merely glows with reflected sunlight. If you were to follow its progress in the sky for a month, you would observe a cycle of phases, which have different appearances, with the moon starting dark and getting more and more illuminated by sunlight over the course of about 2 weeks. After the moon's disk becomes fully bright, it begins to fade, returning to dark about 2 weeks later. Although we know that the sun moves 1/12 of its path around the sky each month, for purposes of explaining the phases, we can assume that the sun's light comes from roughly the same direction during the course of a 4-week lunar cycle. The moon, on the other hand, moves completely around Earth in that time. As we watch the moon from our vantage point on Earth, how much of its face we see illuminated by sunlight depends on the angle the sun makes with the moon. Let's examine the moon's cycle of phases using the figure which depicts the moon's behavior for the entire month. The trick to this figure is that you must imagine yourself standing on Earth, facing the moon in each of its phases. So for the position labeled new, you are on the right side of the Earth, and it's the middle of the day. For the position full, you are on the left of the Earth in the middle of the night. Note that in every position on the figure, the moon is half illuminated and half dark, as a ball in sunlight should be. The difference at each position has to do with what part of the moon faces Earth. The moon is said to be new when it is in the same general direction in the sky as the sun, or position A. Here, its illuminated bright side is turned away from us, and its dark side is turned towards us. You might say that the sun is shining on the wrong side of the moon from our perspective. In this phase, the moon is invisible to us. Its dark, rocky surface does not give off any light of its own, because the new moon is in the same part of the sky as the sun. It rises at sunrise and sets at sunset. But the moon does not remain in this phase long because it moves eastward each day in its monthly path around us. Since it takes about 30 days to orbit Earth and there are 360 degrees in a circle, the moon will move about 12 degrees in the sky each day, or about 24 times its own diameter. A day or two after the new phase, the thin crescent appears. As we begin to see a small part of the moon's illuminated hemisphere, it has moved into a position where it now reflects a little sunlight toward us along one side. The bright crescent increases in size on successive days as the moon moves farther and farther around the sky away from the direction of the sun, which is in position B. Because the moon is moving eastward away from the sun, it rises later and later each day, like a student during summer vacation. After about 1 week, the moon is 1/4 of the way around its orbit, as in position C. And so we say it is at the first quarter phase. Half of the moon's illuminated side is visible to Earth's observers, just like this in the picture. Because of its eastward motion, the moon now lags about 1/4 of the day behind the sun, rising around noon and setting around midnight. During the week after the first quarter phase, we see more and more of the sun's illuminated hemisphere as in position D, a phase that is called waxing or growing gibbous, which is from the Latin gibbous, meaning hump. Eventually, the moon arrives at position E in our picture, where it and the sun are opposite each other. So the sun is here and the moon is in this area. The side of the moon turned toward the sun and is also turned toward Earth. And we now have the full phase. The moon's revolution and rotation. The moon's sidereal period, that is, the period of its revolution about Earth, measured with respect to the stars, is a little over 27 days. The sidereal month is 27.3217 days to be exact. The time interval in which the phases repeat, say from full to full, is the solar month, which is at 29.5306 days. The difference results from Earth's motion around the Sun. The Moon must make more than a complete turn around the moving Earth to get back to the same phase with respect to the Sun. As we saw, the Moon changes its position on the celestial sphere rather rapidly, even during a single evening. The Moon creeps visibly eastward among the stars, traveling its own width in a little less than an hour. The delay in moonrise from one day to the next caused by this eastward motion averages about 50 minutes. The Moon rotates on its axis in exactly the same time that it takes to revolve about Earth. As a consequence, the Moon always keeps the same face turned toward Earth. You can simulate this yourself by orbiting your roommate or another volunteer. Start by facing your roommate. If you make one rotation or spin with your shoulders in the exact same time that you revolve around him or her, you will continue to face your roommate during the whole orbit. As you will see in the coming lessons, the Moon is not the only world that exhibits this behavior, which scientists call synchronous rotation. The differences in the Moon's appearance from one night to the next are due to changing illumination by the Sun, not to its own rotation. You may sometimes hear the backside of the Moon, the side we never see, called the dark side. This is a misunderstanding of the real situation. Which side is light and which is dark changes as the Moon moves around Earth. The back side is dark no more frequently than the front side. Since the Moon rotates, the Sun rises and sets on all sides of the Moon. With apologies to Pink Floyd, there is simply no regular dark side of the Moon. Let's talk about the ocean tides and the Moon. Anyone living near the sea is familiar with the twice-daily rising and falling of the tides. Early in history, it was clear that tides must be related to the Moon because the daily delay in high tide is the same as the daily delay in the Moon's rising. A satisfactory explanation of the tides, however, awaited the theory of gravity, supplied by Newton. These forces differ slightly from one another because Earth is not a point, but has a certain size. All parts are not equally distant from the Moon, nor are they all in exactly the same direction from the Moon. Moreover, Earth is not perfectly rigid. As a result, the differences among the forces of the Moon's attraction on different parts of the Earth causes the Earth to distort slightly. These forces is what we call the differential forces. The side of the Earth nearest to the Moon is attracted toward the Moon more strongly than is the center of Earth, which in turn is attracted more strongly than is the side opposite the Moon. Thus, the differential forces tend to stretch Earth slightly into a prolate spheroid, or a football shape, with its long diameter pointed toward the Moon. If Earth were made of water, it would distort until the Moon's differential forces over different parts of its surface came into balance with Earth's own gravitational forces pulling it together. Calculations show that, in this case, Earth would distort from a sphere by amounts ranging up to nearly 1 meter. Measurements of the actual deformation of Earth show that the solid Earth does distort, but only about one-third as much as water would, because of the greater rigidity of Earth's interior. Because the tidal distortion of the solid Earth amounts at its greatest to only about 20 centimeters, Earth does not distort enough to balance the Moon's differential forces with its own gravity. Hence, objects at Earth's surface experience tiny horizontal tugs, tending to make them slide about. These tide-raising forces are too insignificant to affect solid objects like astronomy students or rocks in Earth's crust, but they do not affect the waters in the oceans. The tide-raising forces acting over a number of hours produce motions of the water that result in measurable tidal bulges in the oceans. Water on the side of Earth facing the Moon flows toward it, with the greatest depths roughly at the point below the Moon. On the side of the Earth opposite the Moon, water also flows to produce a tidal bulge. Note that the tidal bulges in the oceans do not result from the Moon's compressing or expanding the water, nor from the Moon's lifting the water away from Earth. Rather, they result from an actual flow of water over Earth's surface toward the two regions below and opposite the Moon, causing the water to pile up to greater depths at those places, just like the first picture. The Sun also produces tides on Earth, although it is less than half as effective as the Moon at tide raising. The actual tides we experience are a combination of the larger effect of the Moon and the smaller effect of the Sun. When the Sun and Moon are lined up, as in at new moon or full moon in letter A, the tides produce reinforce each other and so are greater than normal. These are called spring tides. Well, the name is connected not to the season but to the idea that higher tides spring up. Spring tides are approximately the same, whether the Sun and Moon are on the same or opposite sides of Earth because tidal bulges occur on both sides. When the Moon is at first quarter or last quarter, as in picture B, at right angles to the Sun's direction, the tides produced by the Sun partially cancel the tides of the Moon, making them lower than usual. These are called the neap tides. Eclipses of the Sun and the Moon. Any solid object in the solar system casts a shadow by blocking the light of the Sun from a region behind it. This shadow in space becomes apparent whenever another object moves into it. In general, an eclipse occurs whenever any part of either Earth or the Moon enters the shadow of the other. When the Moon's shadow strikes Earth, people within the shadow see the Sun at least partially covered by the Moon. That is, they witness a solar eclipse. When the Moon passes into the shadow of Earth, people on the night side of Earth see the Moon darken in what is called a lunar eclipse. Now let's look at how these things happen in more detail. The shadows of Earth and the Moon consist of two parts: a cone, where the shadow is darkest, called the umbra, and a lighter, more diffuse region of darkness called the penumbra. As you can imagine, the most spectacular eclipses occur when an object enters the umbra. This figure illustrates the appearance of the Moon's shadow and what the Sun and Moon would look like from different points within the shadow. If the path of the Moon in the sky were identical to the path of the Sun, the ecliptic, we might expect to see an eclipse from the Sun and the Moon each month. Whenever the Moon got in front of the Sun or into the shadow of Earth, however, as we mentioned, the Moon's orbit is tilted relative to the plane of Earth's orbit about the Sun by about 5 degrees. So imagine two hula hoops with a common center but tilted a bit. As a result, during most months, the moon is sufficiently above or below the ecliptic plane to avoid an eclipse. But when the two paths cross twice a year, it is then eclipse season and eclipses are possible. Eclipses of the Sun. If an eclipse of the Sun occurs when the Moon is somewhat nearer than its average distance, the Moon can completely hide the Sun, producing a total solar eclipse. Another way to say it is that a total eclipse of the Sun occurs at those times when the umbra of the Moon's shadow reaches the surface of Earth. The geometry of a total solar eclipse, as illustrated in this figure. If the Sun and Moon are properly aligned, then the Moon's darkest shadow intersects the ground at a small point on Earth's surface. Anyone on Earth within the small area covered by the tip of the Moon's shadow will, for a few minutes, be unable to see the Sun and will witness a total eclipse. At the same time, observers in a larger area of Earth's surface who are in the penumbra will see only a part of the Sun eclipsed by the Moon. We call this a partial solar eclipse. Between Earth's rotation and the motion of the Moon in its orbit, the tip of the Moon's shadow sweeps eastward at about 1,500 kilometers per hour along a thin band across the surface of the Earth. The thin zone across Earth within which a total solar eclipse is visible, the weather permitting, is called the eclipse path, or this point. Within a region about 3,000 kilometers on either side of the eclipse path, a partial solar eclipse is visible. It does not take long for the Moon's shadow to sweep past a given point on Earth. The duration of totality may be only a brief instant and can never exceed about 7 minutes. What can you see if you are lucky enough to catch a total eclipse? A solar eclipse starts when the Moon just begins to silhouette itself against the edge of the Sun's disk. A partial phase follows, during which more and more of the Sun is covered by the Moon. About an hour after the eclipse begins, the Sun becomes completely hidden behind the Moon. In the few minutes immediately before this period of totality begins, the sky noticeably darkens. Some flowers close up, and chickens may go to roost. As an eerie twilight suddenly descends during the day, other animals and people may get disoriented. During totality, the sky is dark enough that planets become visible in the sky, and usually the brighter stars do as well. As the bright disk of the Sun becomes entirely hidden behind the Moon, the Sun's remarkable corona flashes into view. The corona is the Sun's outer atmosphere, consisting of sparse gases that extends for millions of miles in all directions from the apparent surface of the Sun. It is ordinarily not visible because the light of the corona is feeble compared with the light from the underlying layers of the Sun. Only when the brilliant glare from the Sun's visible disk is blotted out by the Moon during a total eclipse is the pearly white corona visible. The total phase of the eclipse ends as abruptly as it began, when the Moon begins to uncover the Sun. Gradually, the partial phases of the eclipse repeat themselves in reverse order until the Moon has completely uncovered the Sun. We should make one important safety point here. While the few minutes of the total eclipse are safe to look at, if any part of the Sun is uncovered, you must protect your eyes with safe eclipse glasses, or by projecting an image of the Sun instead of looking at it directly. Eclipses of the Moon. A lunar eclipse occurs when the Moon enters the shadow of Earth. The geometry of lunar eclipse is shown in this figure. Earth's dark shadow is about 1.4 million kilometers long, so at the Moon's distance, an average of 384,000 kilometers, it could cover about 4 full moons, unlike the solar eclipse, which is visible only in certain local areas on Earth. A lunar eclipse is visible to everyone who can see the Moon. Because a lunar eclipse can be seen, weather permitting, from the entire night side of Earth, Lunar eclipses are observed far more frequently from a given place on Earth than are solar eclipses. A lunar eclipse can take place only when the Sun, Earth, and Moon are in a line. The Moon is opposite the Sun, which means the Moon will be in full phase before the eclipse, making the darkening even more dramatic. About 20 minutes before the Moon reaches the dark shadow, it dims somewhat as Earth partly blocks the sunlight. As the Moon begins to dip into the shadow, the curved shape of Earth's shadow upon it soon becomes apparent. That's the end of the discussion. I hope you learned something. Thank you and have a great day. Bye.